So in the turning effect of forces chapter, we have a couple of things that we have to know. Let's go through this list first, then I'm going to slowly take you onto the explanations. Describe the moment of a force in terms of its turning effect. Describe simple everyday examples of moments. This is a pretty interesting thing, which this example can have a lot of range. We are going to cover some of them, but technically speaking, it's not possible to cover all of them because there are so many different applications of turning effects. But I'm going to cover as many practical stuffs that I can tell. So, and then state the principle of moments for a body in equilibrium, and then do calculations using the equation moment of a force equals to force into perpendicular distance from the pivot. What does this mean? I'm going to talk about this as well. Do calculations using the principles of moment and describe how to verify the principle of moment. This is an experiment that we're going to talk about after a while. Describe in words the effect of the position of the center of mass this is an experiment. Describe how to find the position of the center of mass of a plane lamina. Describe in words the effect of the position of the center of mass on the stability of a simple object. So we're going to cover all of this and some relevant examples and some explanation that goes with this chapter further beyond the scope of this discussion. I'll be picking up those as well. So if I start, not this one, this one, the applying force, like I've always discussed in the application in the chapters for forces. These are moment chapters, so I'm going to give the heading. You don't have to write these stuffs because this will be available as a video format. You can always go through the video and have a revision if you feel like. Just listen up close. If you have any question, you ask me about it. By applying force, we can do three things to an object. We can move an object, which essentially mean we can accelerate or we can decelerate, or if there is a equal amount of resistive force available, we can make an object to move in uniform motion, or uniform motion means uniform velocity. So this is about motion. So we can move an object, uniform motion. The other thing that we can do is we can deform an object, which we have covered in the chapter of elasticity and Hooke's law. So we can change the shape of an object either by reversible or irreversible or permanent deformation. Two types of deformation we can do. And the third thing that we can do is that we can turn objects, or we can rotate objects about their original orientation to a new orientation. Interesting part for the turning effect is that whenever we're going to discuss turning effect, the question usually will always have a certain point that is described as pivot. This is pivot. I think this is the correct principle. Sometimes people also pronounce it as a pivot. I'm not sure why that is. I know it as pivot. Pivot point is, if it is defined, then we have to assume that this object is capable to rotate about that point, that location, and cannot get away from that location. Let me elaborate what I mean. Let's say this is a rod. I'm showing you a top view. Let's say this is a table. On the table there is a block of wood. On the block of wood there is a screw, and let's say on that screw we have hinged meter rule somewhere, not at the middle, in any location, in such a way that if I apply some force in this direction or apply some force in this direction, this meter rule can rotate about this point. This is the point that we usually talk about as pivot, the stationary point about which an object can go around. Rotating would essentially change its orientation, but this object can never move away from this point. Moving away would mean to actually get displaced from this position. So it can rotate about. There are a couple of things that is pretty important over here, is that to make any object rotate about the pivot point, applied force cannot go through that point. What I mean is that, let's say this is a stationary situation. Let's say there's a table, there is a wooden block, there is a screwed meter rule, and we are about to having it to be rotated. If we apply some force in this direction or in this direction, this object is going to move, works. But what if we apply a force that is directly along the line that passes through the pivot point? For example, if I apply a force along this line out of the object. So let's say I'm going to hold on onto this end of the meter rule, and if I just pull it to the right, will this object start to rotate? That answer is a solid no. You cannot rotate the object if your applied force passes through the pivot point. This is this was for the pulling example. This is equally applicable for pushing as well. For example, if I apply some pushing force onto this ruler along this exact same alignment, let's say something like okay, this is weird. So if I apply a force exactly along the direction of the pivot, I cannot also move it. This is something that you already can understand for the case of a door, which is a much most commonly used hinged equipment that you have used in your life. In my opinion, doors are whenever we apply force to open the door, we do not apply the force that is aimed towards the hinge. So we apply the force at an angle with the hinge. As a result, the door can open or the door can close. But if you try to pull the door away from the hinge, the door is not going to move. Well, we're talking about regular force, not breaking amount of force, or like let's you are one of the Superman or Iron Man kind of person. No, a regular person pulling it away from the hinge, the door is not going to move. If you push it towards the hinge, the door is not going to move either. This gives us one very important idea, is that the turning effect of force is only available as long as the force is applied not aiming or not coming directly away from the pivot point. It has to be somewhat offset or at some angle with the pivot point. This is really, really important. We're going to discuss more about these parts of that, why this alignment thing comes into play with mathematical terms as well. The definition for turning effect of force is very simple, or if I define the term moment, in my next bullet, if I try to define the term moment is defined, I might have told you this earlier, but I'll tell you this again, that to define any physical quantity, there are two different ways we can go for. We can go for a qualitative definition, for example, stating what it is. For example, what is force? You can say that it is the push or pull on any object. That is a qualitative definition, saying what it is. Or you can also give the definition of an object by terms of its quantitative definition. For example, you can always say, for your syllabus, O-level syllabus, force is the product of mass and acceleration of a body, which also works. So for typically, the examiners always like to have the quantitative definition. I don't know the reason, but that's how they work. That's what I have derived from the examiner's report over the years. So moment can be defined in terms of qualitative definition. We can say that it is the turning effect of force on an object, which works. But the quantitative definition goes like this. It is force multiplied by perpendicular distance.
Sir, definition কি equilibrium লেখা লাগবে না?
না, মোমেন্টের ডেফিনিশন ইকুইলিব্রিয়াম আসবে না। ইকুইলিব্রিয়াম আসবে হচ্ছে প্রিন্সিপাল অফ মোমেন্টস, ওটা আসবে পরে। ফোর্স নট পারপেন্ডিকুলার ডিস্টেন্স অফ ফোর্স ফ্রম পিভট। সো এই পুরো জিনিসটা হচ্ছে মোমেন্টের ডেফিনিশন। সো ইফ দ্য কোশ্চেন এভার শোজ দ্যাট ডিফাইন মোমেন্ট or what is moment, you just write this whole thing and you get full marks for that. 1 mark or 2 mark, doesn't matter. In many cases, students forget about this word perpendicular. Don't miss up this word. This is the most key word for the definition of moment, because after a while we're going to see another thing. In the work energy part chapter, which we haven't covered yet, but we'll see that work is also a physical quantity that is also defined as force into distance. And moment is also a quantity which is also defined as force into some sort of distance, but they are not the same. They are different quantities. Work
Sir,
is a
কিন্তু
scalar
SI
quantity.
unit different নোটার।
If you have questions, you can raise hands so that I can pause at a certain point of my lecture and can give you the floor so to take the question. I'd really appreciate that. ঠিক আছে, হ্যাঁ বলো কি বলতেছিলা রোহান?
না, মোমেন্ট আর ওয়ার্ক ডানের এসআই ইউনিট তো ডিফারেন্ট, কিন্তু ফর্মুলা সেম।
Formula same na, SI unit same na. There are difference in both of them, which I was about to go in a short form. I was about to say that. All right. So the SI unit for moment is given as Newton meter, whereas the SI unit for work is given in joule. One is given as the force into perpendicular distance. The other one is given as the force into distance in the direction of the force. So there is a sort of direction involvement, two alternative direction involvement for the definition of moment and work done. although they would always come from the product of two similar quantities. For example, force is force and distance is distance. So this is a measurement of force, this is a measurement of length. So if you think that the unit for moment should be Newton, my Newton looks bad. The unit for moment should be given by Newton multiplied by meter. We write the unit of moment as in this format. So we simply write Newton meter. We do not convert this into joule. Although whenever we will come to work energy power chapter, we'll see that the definition of 1 joule is given by 1 Newton into 1 meter. So if you are working with work or energy, then we are going to use the joule unit. If you are working with moment, then we're going to use the Newton meter unit. These two things are mathematically equal, but quantity wise they are not the same. Why they are not the same, I'll talk about this after a while. You guys know that there are two key type of quantities that we talk about: scalar quantities and vector quantities. Scalar quantities are something that have only the magnitude, doesn't depend on direction at all, whereas the vector quantities which depend on magnitude and direction both. Scalar quantities, addition, subtraction, multiplication, divisions are very simple. These are like basic numbers. You just do it and it's perfectly good. But vector quantities are dependent on their direction a lot. So their addition has to be done geometrically, which we have seen that we have to go for parallelogram rule or triangle rule to find out their summations, the resultant value for two vectors. Similarly, subtractions as well. And as for the multiplication or division of vector quantities, this is also not as simple as scalar quantities. The product of vector quantities can have two type of outputs. Multiplying two vector quantities together, we can have a scalar quantity, for example, that is called dot multiplication. For example, if there are two vector quantities and they are undergoing dot multiplication, we get a scalar quantity. This is something like what is the work is about. Work is a scalar quantity coming from the product of force and displacement. But the multiplication that we are doing to define the work is a scalar multiplication or dot multiplication, whereas the cross multiplication basically gives us another vector quantity, which in this case is the moment. So the reason I'm taking you to this far out in the discussion, to give you an idea that similar quantities multiplied in two different ways of multiplication can give rise to two different quantities, which is a very simple example, a very common example that we have to understand from these topics, because these are both included in your syllabus. Moment is also there, and work is also a part of your O-level syllabus. So that's the basic definition. So if we try to figure this out in terms of some diagrams, let's try to do that. I'm going to be drawing two different scenarios. Let's say 1, 2, and the third one I could draw over here maybe. Let's say all of these three blocks, they are, we're looking at the top view of the object, or if you want to think about the side view, it can be a bit difficult because the weight comes in to play some role. So let's consider these are the top views of objects. So they'll be pivoted at some point. Let's assume that all of these three objects, they are pivoted here. This one is pivoted here, and this one is pivoted here. This one is pivoted here. Yes, Ifat, you have a question?
Sir, could you pen? Because it's not that much visible.
Sure.
Thank you, sir.
Sure. This works, for example?
Yes, sir.
Okay. I will. Sure. Thank you. Thanks for letting me know that. Okay, let's consider these are the three different boxes that we have, and then we are gonna try to apply some forces on them and see how they work. So this is the pivot point, means that this object can move around about this point. If I now apply a vertical force, let's say somewhere exactly over here in the upward direction, in such a way that this force makes a perfect 90-degree angle over here, and if the applied force is d distance away, let's say this is the d distance away from the pivot point, I might as well show the force going all the way up to the halfway point of the object, because this is a general way, standard way to represent forces, not exactly on the border, rather somewhere on the axis line. What I mean by the axis line can be shown like this. For example, I can consider this is the axis line of the object, which is an imaginary line, not drawn with the object, but you can see that this is a rectangular object. So if you think of a midline along the length of the object through the object itself. That's what we call the axis line. So I'm not going to have it over here, but I want you to imagine that. So if we are applying a force over here and if there's 90 degree between them, then the moment is very simple. This would be force multiplied by distance, and that basically is the definition of moment. The reason we are not having any problem because the distance and the force are already perpendicular to each other, which makes sense. What's going to happen if there is a bit of an angle between them? For example, let's say if this force in this position was not applied in that alignment, rather we applied the force in this alignment. For example, let's say in this alignment. So if the force is applied at some angle with the object's axis, then how we're going to deal with this? In the same way that, let's say, the defined distance between the applied force and the pivot point is given as d. So here the angle is no longer 90 degrees. So how can we work with that? One easy way, the typical way to find out how much moment we produce is that we have to find out what is the perpendicular distance of this force from the pivot point. What is the perpendicular distance from this of this force from the pivot point? So we have to somehow draw a normal line from the pivot point onto the force. Now there is a catch. In many cases, for printed figures or given figures, the drawn force line, this is the line of the force. This might not as well be as long, might not be long enough for you to be able to draw the perpendicular. If that's the case, you are always at liberty, and you should try. You can always extend that force. So, for example, in this case, I can extend that force line by a little bit on the other side, and extend that force a little bit on this side. I shouldn't be requiring to do this on both sides. I'm just showing this that this is it is allowed to elongate that force line in both directions if you need to draw some diagram. In this case, pulling it backwards would be good enough for me, but I'm trying to show you that you can do it on both directions as per your requirement. Now we can draw a perpendicular from this pivot point onto the force line. So let me try to draw that with maybe blue. So okay, if I draw a perpendicular line over here, now I can say that there is a perfect 90 degree over here. Now the question is, the force is over here. To get the moment, I need to find out how much is this. This is the part that I need to find out. To be able to find this, let's go for some angle, and we're gonna do some trigonometry. Let's assume that the axis line of the object, I'm showing you this with sky blue color as a straight line. Let's say that this is the axis line of the object, which goes to the axis point of the thing. And if the angle is between the object's alignment and the force is d. So one other thing that, sorry, d now, theta. If this angle is, let's say, theta. Now one thing you need to understand, try to visualize this triangle very minutely, and you should be able to see a right angle triangle where this side, this light blue side, has the known length d, which is the hypotenuse, and this is the what do you call this, adjacent side or opposite side? This one,
Opposite.
Opposite.
this is the opposite side of the angle theta. Beautiful. So we don't know this, so this is our unknown. Let me just give it a name. Let's say I'm going to give this a name, let's say x, just for the sake of discussion. So in this case, our moment should be f into x. Now I need to replace this x in terms of d and theta somehow. Now if you have a look at this right angle triangle, and if I want to make a relationship between the hypotenuse and the opposite, hypotenuse and opposites are related by sine ratio. So I can write sine theta equals to opposite, in this case, which is x, divided by the hypotenuse, which is d. So if I now get the value of x, which can be d sine theta, that's the information. So I'm going to replace this value right up over here, and this will be f m equals to f d sine theta. So what is really important for us to understand that this theta was the angle between the force and the d, not on the outside. Not on the outside কথা আমি কেন বলছি খেয়াল করো, কিছু কিছু কেসে স্পেশালি এমসিকিউতে অনেক সময় ম্যাথ করার সময় টিচাররা যে কাজটা করে সেটা হচ্ছে জাস্ট টু কনফিউজ দ্য কিড, সামটাইমস দে মাইট গিভ ইউ দ্য অ্যাঙ্গেল রাইট আপ ওভার হিয়ার। মনে করো তোমাকে এই বাইরের যে এখানে যে অবটিউজ অ্যাঙ্গেলটা আছে, মনে করো এই অ্যাঙ্গেলটার ভ্যালু দিয়ে দিচ্ছে, মনে করো এই অ্যাঙ্গেলটার ভ্যালু দিয়ে দিচ্ছে হচ্ছে 120 ডিগ্রি। আর তুমি যদি ক্যালকুলেটরে 120 ডিগ্রি বসায় ডিগ্রিতে এই সাম দিয়ে ম্যাথ করো, এই ফর্মে ম্যাথ করো, তাহলে কিন্তু তোমার অঙ্কটা হবে না, বিকজ ইউ হ্যাভ টু হ্যাভ দ্য অ্যাঙ্গেল between the force and the D, not the outer angle, rather the inside angle. This is pretty important for you to work with. In many cases, I mean, এটা আমি তোমাদেরকে স্পেসিফিকলি বলার একটা কারণ আছে যে আমি টু বি অনেস্ট আই মিন if I retract my information a little bit, তোমরা কি all sin tan cos এই জিনিস পড়ছো? এই যে all এখানে all পজিটিভ sin পজিটিভ এগুলো পড়ছো?
Yes, sir.
Yes, sir.
আচ্ছা,
All students take chemistry.
okay, beautiful. They don't although, but anyway, it makes sense. So একটা জিনিস খেয়াল করো, if an angle is theta over here and if an angle over here is 180 minus theta, the sine ratio of both of these angles value is same. Do you know that? What I'm trying to say is, let's say if you are trying to calculate the value of sine 35, calculate the value of sine 35 value কত হয়? Sine, আচ্ছা, first check that your calculator is in degree mode.
0.573.
Sine 35 gives us 0.574. If I do rather round off 0.574. Now, if I do the obtuse angle of this one, so for example, if I do sine 180 minus 35, write this in this exact format in your calculator with brackets and such, and see what do you get.
It's the same.
0.735.
No, you get the exact same value.
Yes.
Yes, sir.
Okay. So the point that I'm trying to make, that even if the question gives you this angle and you use this exact angle in your equation, because it is a sine ratio, this math will work just fine. This math will work just fine because this ratio over here is sine, and sine is able to work with an acute angle and exactly equal amount of supplementary angle. Both of the sine values become exactly equal. But so mathematically speaking, if you use this angle for your calculation, you will also get the correct answer. No big deal. But I highly recommend that you understand that the angle that we usually use over here, that f d sine theta, the theta is supposed to be the angle between them. Yes.
C1 মার্ক পাবে, M1 মার্ক পাবে। যদি M1 মার্ক থাকে এখানে, মেথড মার্ক যদি থাকে তাহলে মেথড মার্ক পাবে।
আচ্ছা,
অ্যানসার মার্ক পাবে, ক্যালকুলেশন মার্ক পাবে। C1 মার্ক পাবে, A1 মার্ক পাবে। কিন্তু M1 মার্ক যদি থাকে তাহলে M1 মার্ক পাবে।
Acha, yeah, I have one of my student who is a pretty genius person named Raja, who is beside me. He just came by to see me. He actually mentioned a pretty good point. সেটা হচ্ছে ম্যাথমেটিক্যাল কোশ্চেনে তোমাদের যে মার্কস ডিস্ট্রিবিউশন থাকে, মনে করো তোমাকে এরকম একটা সাম করতে দিয়েছে, এই অ্যাঙ্গেলটা লেবেল করে দেওয়া আছে, ঠিক আছে? আর মনে করো অঙ্কটাতে মার্ক আছে হচ্ছে 3, এই 3 মার্ক তোমার ভাগ করা থাকবে তিনটা ভাগ, C1, M1 আর এটা হচ্ছে A1. C1 হচ্ছে কোর মার্ক. Core mark means, did you use this equation, or could you actually understand that this is a scenario for which you have to use this equation? If this equation is seen to be used in any format, either by mentioning the variables or by direct application of numbers, I always recommend that you write the first formula first as you are doing your math. If this formula is seen anywhere in your work, you will get the C1 mark. Now, if you do not do the subtraction of 180 minus theta, if you do not use it as 60 degree, then you lose the method mark, because for the method mark you're supposed to use this angle, not this angle. Although the answer would actually match, because you can see that both of these things give you the same value. So if তুমি যদি এখানে 60 ডিগ্রি দিয়ে করো তাও তোমার যে ভ্যালু আসবে, তুমি যদি এখানে 120 ডিগ্রি দিয়ে করো তাও তোমার এক্স্যাক্টলি সেম আনসারই আসবে, which means you are not going to get this M1 mark, মেথড মার্কটা তুমি পাবা না এই জায়গা থেকে, বাট যেহেতু আনসারটা পারফেক্টলি ম্যাচ করবে, সো তুমি A1 মার্কটা ঠিকই পাবা. That's how you are going to be losing mark. The math will be all right, but you'll be losing mark for missing out observation. Do I make sense?
Yes, sir.
ঠিক আছে? আচ্ছা, thank you. So this is the part that I want to discuss over here. So I'll be taking this rectangle a bit out because I have pretty much clamped up this space. So I'll be taking this a bit far out. Let's say, okay, let's make this longer. The third case that we can have is, let's say we have a bar like this, which is pivoted right up over here. Assumed that this is the axis line of the object. This line might not be printed, but you would have to assume this line existing. And if the force is applied in a direction like this, let's say in a direction like this, let me use it for maybe blue. So now what you can see that this is the applied force over here, and the distance d is given to you in the question. So this is the d distance given to you already. This much distance is given to you, and the angle is labeled over here, right over here. F is given over here. Now, once again, if you want to draw the perpendicular distance onto the force, you cannot directly draw any perpendicular line from this pivot point all the way onto this line. So logical step is that we have to extend this line in the convenient direction. You can see that I can never draw a perpendicular line on the force acting line if I go in the downside. So I might actually have to draw a perpendicular somewhere over here. So I'm going to try to extend this line upwards somewhat. It can be as big as you want. The length of this line really doesn't matter, because this is just a reference line for our help to be able to draw the perpendicular line. That's what we're interested in. And then I can draw that perpendicular line. I'm going to use, let's say, green to label that line. So let's say this is the perpendicular line that we have, so that there is a 90-degree angle between these two things. So now you should be also seeing this right angle triangle. This is our unknown x, which we want to measure. So in this case, the moment will be given by force multiplied by x. And you can see that this much distance, this distance, I mean, from here to here, this much was d, and this is your right angle triangle, and this was theta. If I take the opposite angle inside this right angle triangle, this angle can be also said to be theta, because they are opposite angles. So if these two angles are theta, once again, I should actually erase this d, because this is becoming a bit of a distraction, not destruction. So this is the x. So you can also see that in this case also, d is the hypotenuse, x is the opposite side. So pretty much the same sine formula applies, and we can replace the x conveniently with f into d sine theta. The point I'm trying to make over here is that whether your force is applied in this format or the force is applied in this format, either way, we end up with the same mathematical expression, f into d sine theta, where theta is supposed to be the acute angle between the force and the distance that you are working with. এই পর্যন্ত বুঝা গেছে কিনা সবার?
Yes, sir.
একটু ক্লিয়ার হয়েছে সবার?
Sir,
Yes, বলো।
why did we draw the triangle upwards in this one?
Oh,
Upper side.
this triangle?
Yes, sir.
We did not actually aim to draw a triangle. Triangle was not our primary aim. Our primary aim was to draw this thing, perpendicular distance on force. So we wanted to draw this one. Now, we could not draw a perpendicular force unless the force line was present. So first we had to make the force line available to us. For that purpose, we extended the force line in the convenient direction, in this case, which was upwards, so that we could draw a perpendicular from the pivot onto the force line. Together, these two lines made this triangle. Making the triangle was not the primary aim. Primary aim was to draw this line on the perpendicular, so that this line would become perpendicular on the force, which evidently gave us the triangle, right angle triangle, and we could go for the trigonometric manipulation.
Yes, sir, I got it.
Beautiful. আচ্ছা, এটা গেল হচ্ছে আমাদের মোমেন্টের বেসিক ক্যালকুলেশনের পার্ট।
They understand the concept of forces acting at an angle and eventually giving result for resultant force. দুইটা ফোর্স এরকম থাকলে মাঝখানে
হ্যাঁ, ওটা জানে।
তাহলে ওদের ফোর্স ইনভলভিংটাও দেখে। তো এখন দেখালেন হচ্ছে যে ডিসটেন্স দিয়ে কেমনে করব। ফোর্সটাও যে ওইভাবে দুইটা কম্পোনেন্ট নাও যায়, এক্স কম্পোনেন্ট ওয়াই কম্পোনেন্ট, বিকজ মাঝে মধ্যে ওইটা দিয়ে করা হয়
না।
আমি একটা প্র্যাকটিস করছিলাম।
ওলে বলছে নাই। Give us just a second. Okay, Raj actually proposed one more thing that I should teach you, which I was not very prone to, but I was convinced by him. সেটা হচ্ছে, I'm going to show you how to divide a force into its perpendicular components. তোমাদের এই মানে the thing that I'm about to show you right now is not a very highlighted part of the syllabus, but this is something that can always come in handy or useful whenever you are doing your mathematical calculation regarding forces when they are not essentially aligned as the way you would want them to. This is called dividing a vector into its perpendicular components. One is horizontal and this is vertical. They don't essentially have to be horizontal and vertical components per se, but the angle between the two things should be 90 degree. Let me I'll elaborate what I mean. For those of you who aim to perform in any of the physics olympiads or such, math olympiads or such, this would be very helpful for you. So might as well pay some attention. সেটা হচ্ছে, আচ্ছা এক সেকেন্ড পোলাপান।
স্যার
I'm sorry for the delay. My mom and dad are here, so I had to go take care of something. আচ্ছা, যে জিনিসটা বলতেছিলাম সেটা হচ্ছে dividing a force into its perpendicular component or dividing any vector into its perpendicular components. Let me show you a basic right angle triangle. Let's say this one. I would like to have it horizontally flipped. Let's say this hypotenuse of a right angle triangle is labeled as a vector, which is vector. And there is an angle theta over here. This is currently defined as the horizontal component of V. So I'm going to write this as Vx, which will also be a vector, obviously. And this will be labeled as the vertical component of V, which will be labeled as Vy. The idea is that if you sum up these two components, let's say if you do Vx plus Vy, logically you should get V. Now, if you try to apply triangle rule over here, the way triangle rule works, that whenever we use triangle rule, the sum of component vectors gives us the resultant, but the sequence should be start all the component vectors and the resultant, they all should start from the same point. So important bit is that this Vx duration should be in this way and Vy duration should be in this way. Acha, Samira Anis, you raised your hand for a while a bit, I guess. Did you
Yes,
raise your
sir.
hand? Bolo?
Said that the theta must be between the force and the distance, but in the third diagram, the theta was also outside. So is that okay?
Yeah, the theta was also outside on the axis line. That's why whenever I drew this diagram, I labeled this theta inside. I went for this
Where
labeling.
could the theta not?
Bolo, bolo.
Where could the theta? Where could the theta not be in this diagram?
The theta should not be here or here.
Okay.
For example, have a look. This force is over here, and then I extended the force line. So you can pretty much assume that, I mean, here's the deal. Let me elaborate your answer. This diagram, what is the difference between this one and this one, this diagram? There's actually not much difference. I'll tell you what I'm trying to say. This figure shows that if the initial force was placed over here, this is actually representing a pushing force. That by some mechanism, you're going to applying some diagonal pushing force along this alignment. If you replace this force with a pulling force from this point in the same direction, you would get the exact same effect, because having replaced it, converting the pushing force into a pulling force doesn't necessarily change any of the factors, because it's still a vector quantity having the same magnitude and working in the same exact alignment. So having this force over here is exactly same as having the same force acting over here as well. So this vector quantity can be replaced, keeping its alignment same. Do you understand my point?
Yes, sir.
So if we consider that this force practically is not at the bottom of the object, rather, if I assume for the sake of my convenience that this applied force is placed above the object, and then the theta is labeled between the force and the distance, this actually makes the perfect sense, that the angle theta should be the in-between angle between the force vector and the distance vector. All right, getting back to my point. So for this triangle thing to work, I should preferably have this alignment. This is what we call, and also here, these two components should have a 90 degree between them. This is one of the key purpose. I'm going to convert this figure into a different figure after a while. But if you can see it very well, that if I go for a little bit of trigonometry over here, I can find out, I can find out the value of Vy in terms of V and theta, and I can also find the value of Vx in terms of V and theta. How? Have a look. This is the opposite component. So I can write Vy divided by V equals to sine theta. Or you can write that Vy equals to V sine theta. I'm only writing the magnitudes here, so not giving the vector signs anymore. And similarly, if you look for the adjacent component or opposite and adjacent component, then I can write that Vx divided by V gives you cos theta. Or if I subject Vx from here, cross multiplication gives me Vx can be written as V cos theta. So this brings us to a pretty important observation, that the opposite component of the right angle triangle, wherever this theta is labeled, that can be always labeled as a fraction of sine theta of the hypotenuse. I'm using the term fraction because you have to understand what is the maximum value for sine theta. What is the maximum value for sine theta?
1.
1. Minimum?
-1.
Minus 1. Beautiful. Magnitude wise, minimum?
1.
No. Magnitude wise, minimum koto? I mean, sin theta modulus minimum এটা কত হবে?
0.
ম্যাগনিটিউড ওয়াইজ মিনিমাম হচ্ছে 0, কারণ তুমি চিন্তা করো যে 1 হচ্ছে পজিটিভ দিকের বিগ নাম্বার আর 0 নিচেগুলো হচ্ছে নেগেটিভ দিকের বিগ নাম্বার, সো মোর নেগেটিভ, so they are actually small in terms of the sequence of numbers, but magnitude wise smallest value of sin theta হচ্ছে 0, which means whenever any number is multiplied with any sign ratio, this essentially would give you a value smaller than V itself. That's why I'm using the term that Vy can be defined as the sin theta fraction of the V. Similarly, Vx can be said to be the cos theta fraction of v. এই জিনিসটা বোঝা গেছে কিনা দেখো, এই ইকুয়েশন গুলা এবং there is replacement, এই জিনিসটা বোঝা গেছে কিনা? Keep
No,
looking.
sir.
আচ্ছা কোন পার্টটা বুঝো নাই?
স্যার পুরাটা আরেকবার বুঝাবো।
Sure. We have a vector quantity in any direction, whatever. I've started with a convenient direction upward right to make sense, easier sense. And we are trying to divide this vector quantity. And now why we are trying to divide this, that will come in handy after a while. I mean, it used to pore dekhabo. For the time being, mone koro je eta khub dorkari ekta jinish. Assume that. So we are trying to divide this vector quantity into two perpendicular components. Perpendicular means they will be perpendicular with themselves, so that this equation would be held true. If I sum these two vector quantities, these components, these are called components, they altogether will give me the original quantity. So I want to find out the value of these two things in terms of v and theta. So I want to express the vertical component vy in terms of v and theta, which ultimately came from this expression to be v sin theta. And I wanted to express vx in terms of v cos theta, which ultimately came as what? V cos theta, which became v cos theta. So by trigonometry, we got the value of vy and vx. So I replaced those numbers over here. But my aim was to express these two things in terms of v and theta. Nuren, you raised your hand for a while.
No, sir, I got it.
আচ্ছা নুরেন না, আরেকটা কে যেন হাত উঠাইছিলা, একটু সময় যেন দেখছিলাম। আচ্ছা আচ্ছা হ্যাঁ সরি ইটস ওকে। সো হোয়াট হ্যাপেন্স আফটারওয়ার্ডস? সো এখান থেকে আমরা যে জিনিসটা দেখতে পারি সেটা হচ্ছে, এটা হচ্ছে একটা সার্টেন সিনারিও। এটাকে আরো অনেকভাবে ম্যানিপুলেট করা যায়, দেখেন লট অফ ডিফারেন্ট আউটপুটস ফর দিস থিং। বাট to make easier sense to you, I'm going to redraw this triangle rule into parallelogram rule right now. So I'm going to convert this figure into a parallelogram rule. I'm using dark blue for this one. Drawing a similar triangle. Should I draw a triangle? I shouldn't draw a triangle, I should draw a rectangle. Let's say this is the one. I'm going to rub off these edges, because these are going to be my unrequired sides. Why is it not picking up? For this figure as well, resultant vector equals to vx plus vy. Can you?
স্যার আপনি কি ডিরাইভেশন দেখাচ্ছেন?
I'm derivation দেখাচ্ছি। So
Sir,
would you agree that these two figures pretty much represent the same thing but in two different style? This is the triangle rule happening, this is the parallelogram rule happening. Now this parallelogram is not essentially a parallelogram. This parallelogram happens to come out as a rectangle because the angle between the two sides were defined to be 90 degree. Have a look, this is the 90 degree, this one I have 90 degree. The only difference that I have between these two figures is actually the position of the vy. Here the vy was on the rightmost position. I practically slided this line right up over here and got the parallelogram rule. Yes, someone said, sir.
sir, why is v equals to vx plus vy?
This is because of because I want to divide the v in terms of vx and vy. Let me give you a bit similar example to make better sense. তোমরা factorization পড়ছো না?
Yes, sir.
জি স্যার।
মনে করো তুমি যদি 12 কে ফ্যাক্টরাইজেশন করো তাহলে এটাকে কিভাবে লিখবা? 2 into 2 into 3, ঠিক না? এই তো 12 এর ফ্যাক্টরাইজেশন তো এইটুকুই। আর কথা হচ্ছে 12 কে এমনি করে লেখার কি আদৌ কোনো দরকার আছে? 12 তো 12ই, বাট ফ্যাক্টরাইজেশন করলে অনেক কাজ অনেক ইজিলি করা যায় না? যায় কিনা? ফর এক্সাম্পল এলসিএম, এইচসিএফ এগুলো অনেক ইজিলি করা যায় না?
Yes, sir.
That's exactly what I'm trying to achieve. That's something similar that I'm trying to achieve here, is that I am trying to divide this vector quantity, which is labeled as v, into two perpendicular components, so that এই দুটাকে যদি অ্যাড করে দেই আলটিমেটলি আমি আমার ফুল কম্পোনেন্টটা পাবো। তার মানে হচ্ছে these two things, the sum of these two things represents this original quantity altogether. That's also achievable. So this is sort of like, not exactly similar, but sort of, not exactly same, but sort of similar like the factorization of number, but only for the vector quantities. But I'm not going for multiplication, I'm going for addition. I use the example for factorization because this is something that you're used to, which I think would make better sense to you. বুঝছো কি বলছে?
জি স্যার।
আচ্ছা, so what else am I gonna try over here? So আচ্ছা, এই যে এতক্ষণ এতগুলো কাউ করলাম, এই কাউগুলি কেন করলাম, মানে why is this important for us? Let me show you one simple practical example application for this thing. Let's consider this. Let's say this is a horizontal bar which we are seeing from the top view. This is the pivot point, and one force is being applied from on this point in this direction. Let me use straight line. In this direction, let's say this is the applied force, and the question tells you that if I draw the alignment axis of the object, and this is okay, this is okay. So the question tells you that this much gap right over here, I mean from the pivot point to the application point of the force, this is D, and this angle is theta, and they're asking you to calculate the moment of this force. So we have seen one way to do this thing is that we can essentially extend this line backwards, draw a perpendicular, get this whole perpendicular in a right angle triangle, and we can go for moment equals to FD sin theta. We can do that. So this is something that I have described right over here for with these three figures. The alternative way, other than trying to draw the perpendicular on the force, how about we divide the force so that it would have two components, so that one would be perpendicular to this line and they would be aligned to this line. Have a look what I'm doing. I'm going to use green over here to draw a rectangle this big. I'm going to rub off these sides because these are reference lines, not needed for us. I mean needed for the drawing, but not needed for analysis. Now, can I not mark this as f cos theta and mark this as f sin theta? Can I do that?
জি স্যার, করতে পারেন।
এই জিনিসটা বুঝো সবাই। Now here is the deal. This force, I mean the sum of these two things gives this thing. So if we can somehow figure out the effect of both of these forces individually onto this bar, we can find out the combined effect of the F as well. Now, why in the first place should we be interested to do this division? But you should see this F cos theta is working along the axis of the object. So this is actually pulling away from the pivot. What would be the moment produced by this force? Only this force, forget about this one for the time being. Only consider F cos theta. If we pull by some force directly away from the pivot in the same axial line, what turning effect would this force ever produce?
Zero.
None.
None. So the moment produced by this thing, should be zero. So all that left is this one. Now, what you can see over here, magically, there is an 90 degree. So what should be the moment? Perpendicular force into distance. Can we not write this as well?
জি স্যার।
So this brings you the same formula, which was FD sin theta. So it's the same thing. You might feel like that এটা তো আমরা একই জিনিসই শিখলাম, তাহলে এত ভেজাল করে শেখার কারণ কি? This is an alternative way to achieve this similar format. If you wonder why this is important, this actually becomes far too important whenever we are working with multiple forces working on a single object. আমি আরেকটা एग्जांपल দেখাই, তাহলে এটা এই প্রসিডিউরটা কোন কোন কেসে অ্যাপ্লিকেবল সেই জিনিসটা আমি তোমাদেরকে বোঝাচ্ছি। মনে করো let's say there is an object, ঠিক আছে, and this object has a pivot point over here, and you have multiple forces working on it like this, like this. So let's say one of the forces is working vertically upwards like this, and their angles are all given. Let's say this angle is given, and then this angle, this acute angle is given, and this is a 90-degree force. And you are asked to find out the total moment of this whole scenario. Moment can be in two directions, clockwise and counterclockwise, or anti-clockwise. Clockwise means clockwise circle. I mean, I cannot show you clockwise circle. Actually, I can actually show you clockwise circle. I mean, this is clockwise circle, this is clockwise, and this is anti-clockwise or counterclockwise. So moment only can have two directions, unlike other linear vector quantity, because this is circular direction. So we only deal with only two directions. So if we have multiple forces working on a single body, and when we have different angles, if we want to find out the total resultant moment of all of these forces in a single step.
But in real life, there are more than just clockwise and counterclockwise, aren't there?
For moment, there aren't, because whenever we try to determine the moment on an object, we usually don't go for a three-dimensional orientation. We preferably go for a two-dimensional orientation at a time. So we can figure out the moment of multiple forces in two-dimensional orientation, and then we can go for the three-dimensional orientation, and which is called twist. Twist is a different, not different, it is kind of a three-dimensional expression of moment, not applicable for your syllabus. But yes, there can be three-dimensional expression for moment as well.
In A level or beyond?
No, you don't have it in your A levels as well. When this is twist is something that is not introduced in your CIE syllabus at all. But it actually exists. I mean, if you become a structural engineer or a civil engineer, or if you become an architect of furniture or stuffs, you will have to deal with this kind of forces, because these are pretty important forces which actually can control the longevity of a certain product, be it a building, bridge, whatever, furniture, name it. So for this kind of cases where we have to deal with multiple different forces in a single on a single object, having, other than trying to draw individual triangle for all of them and being able to find out the perpendicular distance, that can prove to be quite difficult. Rather than that, you can essentially divide these forces into their perpendicular components and directly go for that calculation. This can prove useful in some cases, but not essentially you will be requiring this. But this is something that I would like you to know. You can decide to forget this or altogether delete this concept from your head, but if you remember this, this will be helpful for you, I guarantee it. The next thing that I'd like to discuss beyond this point of the formula is are some examples of regular life application of moment. Whenever the concept of moment comes in, one of the primary thing that very inherently attached with the concept of moment is what we call mechanical advantage. Now, mechanical advantage is a thing that is not included in your syllabus, but this term is not included in your syllabus. But আমাদের PDF একটা bullet ছিল না, there was a bullet that describes simple everyday examples of moments. This is exactly where mechanical advantage comes in as for your discussion requirement. So this is not taught as an individual term where you have to know this term and be able to express it into variables and everything, but how that helps us is essentially incorporated. So I'm going to give you some examples. One of the very simple example is levers. Not L-I-V-E-R, this is L-E-V-E-R. L-E-V-E-R means lever, that is something that by which you lift objects or something like that. And this is something that produces chemical for your body. So these are two different things. Don't make that spelling mistake. It's important. So the idea of lever is very simple. It goes like this. Let's say there is a heavy object. Let's say there is a almirah. These are the legs of the almirah. This is filled up with iron for whatever reason, extremely heavy. You cannot lift it up. This is the ground, but you need to somehow move it, or you need to somehow rotate it a little bit. So what we can always do is that we can use a long enough rod to stick up over here, which has to be strong, maybe a metal rod or something like that. And we can place a support system or something that is called a pivot point or বাংলায় বলে কিলক, so if you might not know this term, we can have a rod attached over here and give it a support point over here. So what's going to happen, whenever we're going to apply force over here, this end is going to go up, but beauty is going to be the beauty is that pushing it down will be far too easier compared to pulling it up manually. So why is that? Because the way moment works is that I mean, whenever we'll be pulling it down, this will be going up, but you have to understand, if you think for the alignment of the object, if we pull this object down by a huge amount, let's say if we make this bar perfectly horizontal, when this thing would have rotated a little bit to the left. So I'm not gonna draw this alignment of this object because that could prove to be pretty difficult for me to draw in paint. But when this horizontal bar, this bar becomes horizontal, you can see that this end moves by a huge distance, whereas this distance moves up by a very small amount. So we are going to have a huge amount of advantage of force, because it is important that we are basically rotating this rod about this point. We are basically rotating this rod about this point. So let's say we are going to rotate this rod by a moment of 10 Newton meter. I'm just assuming this number without any previous experiment. So let's say we're going to have this at 10 Newton meter. If it so happens that this length of the rod from the pivot all the way to this application point is, let's say, 10 meter, and if this much is only 1 meter, then to produce a 10 Newton meter clockwise moment along this line, we only have to apply 1 Newton force over here, whereas this thing is also going to have 10 Newton meter moment, but this thing would be able to push the almirah up by a value of 10 Newton. So by applying 1 Newton force, you can obtain 10 Newton of force back, because the ratio of these two things is 10:1. This is what makes it beautiful, that levers can actually multiply the force based upon how much is your applied how much is your load side length of the lever, and how much is your application force side length of the lever. This ratio can give you a huge advantage. So this is one of the very common practical example for regular life experiences. এখানে আমি একটা সিম্পল আইডিয়া তোমাদেরকে বলি, যেটা তোমাদের বুঝতে সুবিধা হবে। সেটা হচ্ছে application of levers are always, or lever like mechanisms are always handy whenever we have a longer application side and we have a shorter load side. This is the part of the lever that we're calling the load side. This is the part of the lever that we're calling the application side, or the force side. So if the force side is longer, then you can obtain a bigger force on the load side or application side by applying, on the load side by applying a smaller force. So this ratio is going to hold up. So what I'm trying to mean is that moment should be equal on both sides. So let's say moment on the load side should be equal to moment on the force side. So these two things, okay. So these two things, force on the load into distance of the load side should be equals to force on the applied force side. So force on the force side multiplied by the distance on the force side. So these two ratios can always work out. There is another formula for this one. This formula is actually said to be something else, which is called principle of moment. সেটা আমি একটু পরে দেখাচ্ছি. But lever is basically a very common regular life experiment instrument that you use. আচ্ছা, crowbar পরে দেখাবো, সমস্যা নাই। crowbar ওদের actually example আছে. Kids, do you know what is a crowbar?
Sir.
Crowbar.
Like thing.
Crowbar.
Yes, sir.
Yes, sir. we know.
This thing. It's actually a
Yes,
single
sir.
one. It's a
Sort
single
of
one.
lever device.
It also works under the principle of lever, but there is a 90-degree shift of forces. I'm going to show you what that is. How does that work? Let me just show you how a crowbar looks like, and I might as well take it from there. Hold on, তোমরা কি লেকচার বুঝতেছো? অনেকেই রেসপন্ড করতেছো না, অনেকে কোশ্চেন করতেছো, but is it making sense so far, everyone?
করছে।
Yes, sir.
Yes, sir.
Yes, sir. Obviously, sir.
আচ্ছা, না বুঝলে কোশ্চেন করো
সবাই
or
মনে
raise
হয়
your hand.
bored
I'll
হয়ে
definitely
গেছে।
give you time to for ask your question. No big deal. These are the things that is called a crowbar. These are the things that usually show up in video games to in a lot of video games to kill zombies and stuffs. Anyway, crowbars are usually used to hook up nails or objects from one place to another place. Crowbar also uses the I principle of lever, but there is a 90-degree shift. Let me explain what is that 90-degree shift. Let me explain what is the 90-degree shift. I'm going to pick up some image so that I can actually show you.
Over vector লেখা স্যার
This is the lever mechanism in a different format. There it is. This is actually, I'm trying to get a specific figure to make sense with you, but I might not get that, so I might as well draw that. Searching this is taking longer than I could have drawn, so I'm gonna go for the drawing. Don't worry. The thing for crowbar is, let me draw the crowbar with maybe ash color. Mone karo, let's say this is a wooden block, wooden surface where there is a nail. This is a nail that is stuck in the wooden block. We want to get this out, so we need to apply some upward force on this one. A crowbar, let's say drawn with brown because I'm trying to differentiate, would be placed over here in this alignment. I'm showing you the side view, that's why the gap between the crowbar is not visible. So gap between the crowbars means this gap that I'm talking about. So we are placing the nail in this gap and holding that crowbar in this fashion. So what's going to happen after we fix it up in this manner? We are going to pull this crowbar on the left. So this is a horizontal force. Using this corner of the crowbar, using this corner as a contact point of pivot, this end is going to start pulling this up. So you can see over here, for this figure, both the forces were vertical. This was being pulled downwards, this was being pushed upwards. But over here, this is also working as a lever, but because the lever is 90 degree rotated on in its structure, applying a horizontal force is given an output of vertical force. Do you understand what is happening here, Olaban?
Sir, if we pull the crowbar completely parallel to the ground, then I don't think that will happen. We have to pull it like a bit angularly towards the ground. Like, at least that's how I have done it.
Well, it actually depends on how much angle do you have on the crowbar. I mean, there can be a lot of different. What you actually said is a very good consideration point. For example, have a look at these crowbars. This crowbar is not essentially perfectly 90 degree. Do you see that? There is more angle than 90 degrees. So what this figure essentially tells us that if there is a nail over here, let me draw another nail by ash color. So there is a nail over here, and if we're using one of those carved crowbars, we have to place that crowbar in this fashion. We have to place that crowbar in this fashion. That's how the initial position of the crowbar is gonna be. And then you can either pull it to the left or you can pull it exactly perpendicularly in this way. Now the idea is, if you pull it horizontally, you're gonna have to pull more strongly compared to if you pull it at some angle. The reason the crowbars are designed with some angle is because when people are working with them, it is easier for our hand to extend to that point and pull it by our muscle, being our body at stationary. But if you really want to pull it as a perfect horizontal force, you might actually have to place your body in such a position so that your hand element is perfectly horizontal. That can lead to some slow processing of the work. That's why this angle is over here. Another advantage is that if you want to lift up this nail completely, you have to pull this crowbar all the way to the ground to make this happen. Now, when someone is working, making a crowbar go all the way to the ground would require them to sit and push it to the ground. That can prove to be difficult as well. But having this angle, you might as well rotate this crowbar by up to a certain angle, but not all the way to the ground, still having the crowbar in your hand, and this nail is gonna come up pretty easily. So that's another reason. But what I'm trying to show you over here, that because of the design of the crowbar, because of the angle that exists between the force side and the load side, these two forces are not in the same alignment. We are trying to achieve a vertically upward force, but the applied force will be in different direction. Does that part make sense? Hello?
Sir, could
Yes,
you
sir.
repeat?
We are trying to achieve a vertically upward force to lift up the nail, but the applied force on the crowbar can be horizontally left, can be diagonally upwards. When the crowbar rotates a little bit more, it can still be, for example, when the crowbar is in this position, let's say the nail is halfway up from the ground, and now the crowbar is aligned in this orientation. Let's say this is the crowbar lining, and and the crowbar is now in this alignment. So now we have to apply the force in this direction. So as the nail is going to lift up, we can change the direction of our force so that we can always get a vertically upward force. That's the point that I'm trying to make. So the difference between these two figures is that for this figure, the applied force was vertically downwards, the obtained force was also vertically upwards because the rod was perfectly straight. But because the crowbar has an angle within its structure, the applied force is vertically upwards, where the obtained force is vertically upwards, but the applied force can be in a lot of different directions depending on the exact orientation of the crowbar at any instance. বুঝছো কি?
Yes, sir.
স্যার
বাকি
এটা
সবাই?
হ্যামারের এন্ডে থাকে না?
Hammer ends can have a lot of different things depending upon the purpose of the hammer. All hammers don't usually have crowbars. Some hammers can have pointed ends, some hammers can have ball peen hammer. They can vary, but it is possible to have this attachment at the end of a hammer, typical hammer. Yes. Bangladesh actually আমরা ball peen hammer দিয়ে কাজ করি খুব কম because we don't have that level of in my opinion, what can I say, craftsmanship level, so we don't bother about that. But ball peen hammers can prove to be pretty useful for certain cases. আচ্ছা, এরপরে যে জিনিসটা, আচ্ছা এরপর আরেকটা এক্সাম্পল যেটা লাগবে সেটা হচ্ছে I'm going to talk about a little bit about scissors. How does scissors work? Let me pick up a figure for scissor. Drawing up a scissor can be a bit difficult for me. Keypad. Yeah, beautiful. A scissor has showed itself. Which one do I take? This one?
Copy image paste.
হবে? আচ্ছা. Now, here comes the idea for a scissor. We will always put our fingers in these two positions, here and here. We're gonna push it down, and whatever we are trying to cut is going to be placed between the two jaws, let's say somewhere over here. So in this case, this is the length of our applied force. So we are applying force by this much length, and the load is experiencing the force by means virtue of this much length. So here also we have a bit of mechanical advantage because the applied force side is longer, and the obtained force side is smaller. Or in other terms, I can say that it is much easier to cut objects through a scissor the closer you put it to the screw or the nut in this case, which is working as the lever for these two arms of the scissor. So if you put it pretty or press on the far end, you have to press it pretty hard. It's not very much, you cannot experience it much if your scissor is quite sharp, but when the scissor become dull, you can actually experience it. That for a dull scissor, it is easier to cut objects when you place it close to the bolt over here, not on the end. That can prove to be quite difficult for not so sharp scissors. Why sharp has an effect of the cutting experience. That is another important factor that we can discuss in the pressure chapter. So I'll pick up the scissor example at that point once again, that why is cutting experience, I mean, what is the difference between a dull scissor and a sharp scissor, and how does that actually affect our experience? We're going to talk about that in that chapter as well. Other things that can involve for regular life example for moment application can be wrench, which is also similar like a lever. Actually, I can show you a nice figure for the wrench. I think I have it in the MCQ worksheet. Moment. For example, this is one of the MCQ paper for the moment chapter. I'm just showing you one simple example. Let's say if you have a look at question number 3, just have a look at question number 3. A driver's foot presses on a steady force, presses with a steady force of 20 Newton on a pedal in a car as shown. What is the force F pulling on the piston? So whenever this lever is pushed down by 20 Newton, this is working 20 Newton into 40 centimeter about this pivot. So if you think that whenever this thing will be pulled, this will be going down and be up, and it will rotate about the pivot in an anti-clockwise direction. So this side is producing a total of 20 Newton into 40 centimeter, which is 800 Newton centimeter of moment. So if I go ahead and try to do this math, I might as well take this on, select, beautiful, paste. Please cover this is not needed. So in this case, the anti-clockwise moment produced by the feet along with this entire lever arm is 20 into 4. I'm not writing the units because here this length is also given in centimeters. So both the centimeters are similar. That's why I don't have to bother about unit. But if this was not given in the same unit, I would always have to work with exactly same units on both sides. So this moment should also be equal to the moment available on the other side, which should be F into 5. So by now you can very easily find out the value of the force on this piston by calculating this force. How much is this gonna come? 800 divided by 5, which should be 160 Newton.
160.
Exactly. So you can see that by pressing this lever by only 20 Newton of force, we can achieve a force of 160 Newton on the piston. That's 8 times bigger force. So the mechanical advantage for this setup is 8. The reason it is 8 is because the ratio between these two sides is 8. So the loads, the force side is 40 centimeter and the application side is 5 centimeter. So this length is 8 times as big as this one. So you could multiply the force by 8 times and get a much bigger force. This is one example for practical use for the forces. So this is what they mean by that line, that be able to use those things for regular life calculation and so on. And wheelbarrow is also another example for moment cases. Lifting up a load of this much can prove to be pretty difficult for a regular person, but whenever you place it in a wheelbarrow, you actually have to lift up a much smaller force compared to exactly what you put into the wheelbarrow. For example, in this example, you can see that this is the wheel of the wheelbarrow. So this point is going to work as the pivot for the whole setup. We have placed something over here, which is a total weight of 150 Newton, and the handle's end is over here. So whoever is going to operate this wheelbarrow to move around, they are going to lift up the wheelbarrow by lifting up this end. Now the question is, how much force do they have to lift? Do they have to lift full 150 Newton? The answer is a no. Let me show you how we can achieve this. Quick example. So if you're trying to calculate this, you have to see, this is your applied force, this is the other force. So I can write up the equation. F1 D1 equals to F2 D2. F1 D2 is both the same. This actually comes from the principle of equilibrium of moments. It I mean একটু পরে দেখাবো, but the math works in the same way. What is really important, I mean এই কোশ্চেনটা করার সময় স্টুডেন্টরা ভুল করে কথা সেটা বলতেছি. These D's are always perpendicular distances of the force from the moment. If you don't think that this is a correct formula, I might also write this formula in a much more precise form, which might as well be f1 d1 sine theta 1 should be equals to f2 d2 sine theta 2. Now you might wonder এগুলো sin theta এর কোথা থেকে আসলো? Sin theta আসছে কারণ হচ্ছে মোমেন্ট এবং ফোর্সের মধ্যে যদি 90 ডিগ্রি রিলেশনশিপ না থাকে, if the force and the distance are not at 90 degree with each other, we have to take the sin theta in the equation. But for this figure, we don't have this trouble because you can see 150 Newton with 0.75, 90 degree. F Newton with this length information, also 90 degree. So both of these sin theta is sin 90, which equals to 1. This is also sin 90 equals to 1. That's why we could get rid of this equation, with this sin theta, and could only work with this primary equation, which works. Now, এই কোশ্চেনটা স্টুডেন্টরা সবসময় কারেক্টলি লিখে, ভুলটার কথা হয় তোমাকে দেখে বলতে আসি। What was D defined as? What was the definition of D? Let me show you to help you remember. Read.
Perpendicular distance.
Of force. Check this out. Really important. From the pivot, right? So 150 Newton, for the 150 Newton force, a bit more, okay. For the 150 Newton force, the perpendicular distance is 0.75. So I'm going to write this up. 150 into 0.75 works. The next force is F, which I want to calculate. Now my question is, what is the distance of this force from the pivot? Is this 0.75?
Is 0.75 plus 0.75.
Exactly. I could have directly written the sum format, or I could have written this is 1 multiplied by 2. I could have written in addition form. Any way you write doesn't matter, but it is important that you a force perpendicular distance হচ্ছে এই পুরোটুক, আর এই force perpendicular distance হচ্ছে এইটুক. So these D's are the perpendicular distance of the force from the pivot. স্টুডেন্টরা খুব কমনলি যে ভুলটা করে, এই যদি ভুল করে এমসিকিউতে, তারা দুইটার জন্য 0.75 বসায়। এটার জন্য তারা 0.75 দেখে এটা বসায়, এটার জন্য তারা 0.75 দেখে এখানে 0.75 বসায়, আলটিমেটলি ম্যাথটা ভুল হয়। বাট এই ফোর্সের পারপেন্ডিকুলার ডিসটেন্স কিন্তু 0.75 না, বিকজ এই ফোর্স থেকে আমাদের পিভট পয়েন্ট মানে হুইলের সেন্টার পর্যন্ত পারপেন্ডিকুলার ডিসটেন্স হচ্ছে এই পুরোটুকু। এই জিনিসটা কি বুঝে গেছে সবার?
জি স্যার।
Can a nail cutter be an example for of movements? Yes. Nail cutters are a very good example of lever. It's a very good example because a nail cutter works like this. There is this cutting heads. This is a pinch over here, and there is usually a very strong nail, an actual metal nail, which is pivoted over here by a handle, which pivots over here, and this is the part which goes on, and we place our finger over here and push it down, and the other nail inside here, and we cut it over here. So what happens whenever we push this down, this lever pulls it up, so this jaw pushes it up and this end pushes it down. So this one is pulling it up and this one is pushing it down. So this side is going down and this one is going up. As a result, it produces immense pressure on the nail at this contact point, and we can cut the nails. Yes, nail cutters are very good examples of movement. Asif Irfan, very good pick. Yeah. Well done. So this was just another example. The next thing that I'd like to discuss, we still have time, that is principles of moment for equilibrium. Now let me first come to the idea for equilibrium. What is equilibrium? Equilibrium তোমাদেরকে নিয়ে আমি আগেও আলাপ করছিলাম, but let me just refresh your memories a little bit. Equilibrium of an object means its motion parameters are not changed. In more simpler terms, I can say an object is in equilibrium if the object's velocity is unchanged. What does this mean? A stationary object remaining stationary is in equilibrium because initial velocity was 0, final velocity is 0, equilibrium. An object moving with constant velocity means moving with a constant speed in the same straight line without any angle direction change or without any value change of the speed. That object, as long as the movement keeps on happening, is also in equilibrium. Any object that spins about a certain spins about its own axis at a certain angle. About its own axis, important. For example, the Earth. Earth is rotating about its own axis with a time period of 24 hours. Kids, do you understand this sentence? Earth rotates about its own axis with a time period of 24 hours. Do you understand what I mean?
Yes.
ঠিক আছে, so পুরোটা একবার রোটেট করতে সময় লাগে হচ্ছে 24 hours. I'm not talking about the orbit, I'm talking about Earth's axial rotation. This rotation is also uniform because this is not affected by any external factors. Well, if you think in astronomical factors like the gravitational pull of sun, the effect of the moon, and asteroids hitting the Earth's surface every once in a while, they do actually impact, have some impact on the duration of day. They actually do, but consider those factors as minimal for our discussion. So Earth's rotation about its own axis is unaffected. It is not speeding up, it is not slowing down. So this motion can be also said to be in equilibrium. But Earth's orbit around the sun is not in equilibrium. Earth is going around the Earth at a constant, the Earth is going around the sun. If you consider it to be a circular orbit, which it is not, but let's say for the sake of discussion that it is a circular orbit, that whenever the Earth goes around the sun, it goes around the sun, it covers the entire circumference in a duration of about 365 days. So it has a uniform speed, but is the velocity constant? Think about it. It's a circular motion. Can the velocity be constant in a circular motion? Is it possible?
No.
It's not possible. Why? Even though the magnitude of the speed may be constant, but the duration is always changing. Other than the duration having changed, you cannot have circular motion. So we cannot say Earth is altogether in equilibrium because Earth is being affected by the gravitational pull of the sun and is going in a circular orbit. But the axial rotation of Earth, that is in equilibrium because that is not being sped up, that is not being slowed down, something like that. Kids, I want you to understand one thing very carefully. তোমরা লাটিম চিনো?
Yes, sir.
Yes.
Yes, sir.
ঘুরাতে পারো কে কে?
পারি না।
আচ্ছা, শোন না,
আমার ছোট ভাই পারে।
Latin ঘোরানো is an acquired skill. You don't get it from your mother's womb, so not a big deal. সমস্যা নাই, আরো ছিল, their number used to be go around 40 before I
ক্লাসে যখন পড়াইতেছিলেন তখনই 22 জন ছিল অলরেডি ক্লাসের মাঝখান থেকে 4 জন গেছে
আচ্ছা kids are allowed to leave at my class at any time.
নাইস
If you're not interested to study, you can leave.
hope that work thing university
But yes, the test will happen and then you'll have to give reasons for not being able to do stuff. And lectures are uploaded back into the YouTube, so it's not a big deal. Okay, Latin কথা বলতে সেই জন্য I wanted to give you a certain example and I want you to understand. The way a top is spun, the way a top is spun is that we first want a piece of string around the top. We have it in our hand, then we throw it onto the ground, and as the top travels towards the ground, the tension of the string unwinds the top and gives it a very high rotation. Consider the friction of the ground negligible. Consider that in that manner. Let's say the friction of the ground is negligible. As long as the string is any loop of the string is around the top and the top is continuing its journey towards the ground, there is a continuous force onto the top's body on the circumference of the top to make it go around. Continuous force. That force is continuously speeding up the rotation. That is a moment that exists on the top which is causing it to rotate faster. This type of moment is what we call unbalanced moment. Unbalanced moment. Very much similar to unbalanced force. Do you remember what is unbalanced force? Anyone?
Yes, the resultant isn't zero.
Resultant isn't zero. Beautiful. So this is a moment, this moment that is caused by this force is an unbalanced moment. because this moment is speeding up the rotational speed of the or the spinning of the top. Now, the instant, let's say that that string has come to your hand, or the string is completely wound off from the top's body, and the top is now has landed onto the ground, and considering the friction of the ground is negligible for the sake of example, at that point the rotation of the top would be uniform. If you consider the friction of the ground negligible and the air resistance negligible as well, this top should be able to maintain its rotation for an indefinite period of time because there is nothing stopping it. This is an example of balanced scenario or equilibrium scenario. So what I'm trying to tell you, moving objects can be at equilibrium. Rotating objects can be also at equilibrium. Objects which are not at equilibrium are either accelerating or they are speeding up in their rotation or slowing down in their rotation. Change of state is what makes it not in equilibrium. Unchanged state means in equilibrium. কথাটা কি বোঝা যাচ্ছে? আমি এটা এভাবে বোঝানোর রিজনটা হচ্ছে sometimes students always think that stationary objects are in equilibrium, unstationary objects are not in equilibrium. No, it's nothing like that. Moving objects can also be in equilibrium. Rather, most moving objects are in equilibrium. বুঝছো কি বলছি বলাবান?
Yes.
Everyone else, please respond. যারা আছো, give me some notion, like speak up or write yes in the chat window.
Yes, sir.
Yes.
Do you understand the concept of equilibrium properly?
Yes, sir.
Yes, sir.
Okay, beautiful. So the idea is that if we want to have equilibrium of an object, if an object has to be in equilibrium, we have to fulfill two primary reasons. One, we have to have resultant force on the object to be zero. It has to have equilibrium of forces. Second, it has to have resultant moment equals to zero. Resultant moment has to be also be zero. Whenever both of them, not either of them, whenever both of them are satisfied, only then can we say an object is in equilibrium. If either of them is non-zero, the object is not in equilibrium. Simple. এখন resultant moment zero হওয়ার basic meaning হচ্ছে on any object sum of clockwise moment should be equals to sum of anti-clockwise moment. এই হচ্ছে basic আমাদের equilibrium of moments এর or principle of moment এর basic expression. That যে কোনো অবজেক্টের উপর total clockwise moment should be equals to total anti-clockwise moment if the object is in equilibrium. এইটাকে ইউজ করে আমরা অনেক ডিফারেন্ট সাম করি এবং এই সামগুলো আমরা আস্তে আস্তে আরো সামনে গেলে দেখব। এখন ক্লকওয়াইজ মুভমেন্ট এবং অ্যান্টি ক্লকওয়াইজ মুভমেন্ট ডিটেক্ট করার একটা সহজ বুদ্ধি আছে। সহজ বুদ্ধিটা আমি তোমাদেরকে বলতেছি। সেটা হচ্ছে, আমি একটা সিম্পল এক্সাম্পল দেখাই। I'm going to do this math in detail, so let me pick up this math. This is going to be a pretty elaborate math. I think this math is somewhere over here in our lecture PDF, I hope. তোমাকে তোমাদের বুকলেট থেকে নোটসগুলো পড়ো কখনো? This thing, like,
Yes.
does it help? Sharita?
Yes.
She has poor handwritings at times as well, but she's good, organized.
Then university had.
কই জানি যেতে যাচ্ছি। আচ্ছা, মোমেন্টের ইলাস্টিসিটি এখানে। তোমরা ইলাস্টিসিটি চ্যাপ্টার তোমাদেরকে তো আমি হাতে পড়াইছি, এই নোটস থেকে কিছু দেখাই নাই, বাট এভরিথিং দ্যাট আই ডিড টিচ ইউ ইজ অ্যাকচুয়ালি ইন দ্য নোট অ্যাজ ওয়েল। ফর এনি অফ ইউ or which should be every one of you who have gone through the notes, you should be seeing that. If any part of the notes doesn't make sense at any part of your studying these up, you can always bring them up in the class. Sir, এত নম্বর পেজের এই পার্টটা বুঝি নাই বা এই জিনিসটা একটু কনফিউজিং বা এই পার্টটা আবার বুঝাই দেন, ভুলে গেছি, whatever. I'll always respond to your requests. Here's a simple example. Have a look. Find the force F if object is in equilibrium. Find the reaction force of pivot on the object. This is a very simple. This is the first mathematical question of the moment chapter. First we had this thing, then conditions of equilibrium. These two. So এখানে m হবে। আচ্ছা এটা পোলাপান তোমাদের তো প্রিন্ট করে দিয়ে দিছি। এটা একটু সবাই m বানায় নাও। Pull up your note. Make this capital F, this one capital M. বুঝছো কি বলছে? Pull up the class note and do this correction right now. This
Sir,
is
what's the page number?
This is on page number 29.
স্যার
বলো
কি করব আরেকবার একটু বলবেন?
এই যে এখানে পড়ো, পড়ে দেখো বুঝো কিনা। Conditions of equilibrium. Any object is in equilibrium if resultant force is 0. তারপর আবার কি লেখা আছে? Resultant force is 0 আবার লেখা আছে না, এটা resultant moment হবে। এই f টাকে ক্রস করে ক্যাপিটাল M লেখো, বা এই পুরো লাইনটা কেটে দাও, নিচে লিখো সাম m, something that I did over here. এই যে এইটা বুঝছো?
জি স্যার।
Acha, let's look at this question. Find the forces if if object is in equilibrium. So this is an object which is pivoted here. 30 centimeter away from the object, we are applying an upward force of 300 Newton. 600 Newton, 60 centimeter from this object, we are applying a downward force of F. The question says the object is in equilibrium, so you have to find out what is this force F, which means total clockwise moment should become total anti-clockwise moment. Now, to determine what direction of movement does a force create, the simple way to understand this, whenever you are trying to determine the direction of a moment produced by a force, আবার বলতেছি প্রথম থেকে খেয়াল করে শুনো, whenever you are trying to determine the moment direction produced by a force, consider for that time being that is the only force working on the object. All the objects are absent. Consider that for the time being, and try to visualize in which direction your object is going to rotate under the effect of that force only. For example, this is the pivot point. This is your object. If only the 300 Newton force is working on this bar, in which direction is the bar go move? Is it going to move up or is it going to move down?
Up.
It's going to move up about this point. Sorry. So that just didn't happen. Never mind. So this is going to move up. So as this bar is going to move up, it is going to rotate anti-clockwise or counterclockwise about this point in this manner. So this 300 Newton is producing an anti-clockwise moment. Here's this. In this question, 300 Newton produces anti-clockwise moment, and F itself produces the clockwise moment. Because if you consider only under the effect of force F, if this 300 Newton force is not working, assume that only F is working here. In that case, this is going to only pull the bar downwards, and as a result, this will make this thing to go downwards. So this will be a clockwise rotation. So that's how we determine the direction of the moment produced by a force, considering one force at a time. So this is what we remember. To understand which force produces what kind of moment, we need to consider one force at a time and try to visualize how the object would rotate because of this force. Acha. Then comes the equation. 300 into 0.3, which is the anti-clockwise moment. 0.3, we have given 0.3 because we're converting the centimeter into meters. You can do this, or you can sometimes not do this if all the units of the lengths are equal, which is also okay. Equals to 0.3 plus 0.6. এখানে স্টার মার্ক দেওয়া আছে, এখানে ভুল হয়। বুঝছো কোথায় ভুল হয়? Students sometimes only give f into 0.6, but এটা কিন্তু f into 0.6 হবে না, কারণ আমাদের এই what is the distance of this force from the pivot point? This total thing, right? This total thing. So you have to add these two distances because the force is actually total 30 plus 60 centimeter away from the pivot point. So you have to add these two distances. Students commonly শুধু এইটুকু লিখে এটা লিখতে ভুলে যায়। So এই পার্টটাতেই ক্যালকুলেশন এররটা হয় most commonly, যাদের ভুল হয়। সো এই ভুলটা নিয়ে কেয়ারফুল থাকবা সো দ্যাট এই ভুলটা আমাদের না হয়, and then we can easily calculate this is the 100 Newton force that we can have. আচ্ছা, then comes the next part. এই পর্যন্ত বুঝা গেছে সবার?
Yes, sir.
এক্সাম্পলটা বুঝা গেছে? সিম্পল ওয়ান। আচ্ছা, নেক্সট কোশ্চেনটা দেখি। Next question will say find the reaction force of pivot on the object. And what does this mean? What it means is that if this object is in equilibrium, we have to satisfy two logic. Resultant force should be zero, resultant moment must also be zero. একটা জিনিস দেখো, এই ফোর্সটা আপওয়ার্ড ফোর্স হচ্ছে 300 নিউটন, আমরা ক্যালকুলেট করে পাইলাম এফ ফোর্সটা হচ্ছে ডাউনওয়ার্ড 100 নিউটন। এই দুটো ফোর্সকে একটাকে পারফেক্টলি ব্যালেন্স করতেছে ইন টার্মস অফ ফোর্সেস অনলি। You have 300 Newton upward force, you have 100 Newton downward force. Do they balance each other?
No.
They don't balance each other because they are not equal to each other. They are in opposite direction, but they are not equal to each other, so they are not balancing each other. Which means if the object has to be in equilibrium, this pivot point should also apply on this bar the additional required force for it to become in equilibrium. Simple. এই অবজেক্টটাকে ইকুইলিব্রিয়ামে রাখার জন্য অ্যাডিশনাল যতটুকু ফোর্স লাগবে পিভট ওই ফোর্সটুকু প্রোভাইড করবে। সো হ্যাভ আ লুক, they have a look at this statement. To stay in equilibrium, resultant force equals to 0 must happen. Here 300 Newton works upwards and 100 Newton works downwards, so this object experiences a 200 Newton force upwards because of these two forces. The hinge or the pivot must provide a force to perfectly counterbalance this force. So the reaction force of the pivot on the object is 200 Newton upwards. So now if the pivot provides 200 Newton upwards, high
downwards,
এটা ভুল হইছে, এটা ডাউনওয়ার্ডস হবে, সর্বনাশ। বলো এটা কারেকশন করো। এটা ডাউনওয়ার্ডস কেন হবে বুঝতেছো? The resultant of the available force is upwards, so you want to counterbalance that force. Pivot should apply an equal and opposite force so that the resultant is 0. So the reaction force of the pivot on the object is 200 Newton downwards. এটাকে downwards বানা, I should also correct this right here. Okay, now I need to do something else. Let's copy this up. And have it in a bit smaller font size. And it should have this is pretty important.
white font দিয়ে দেন,
হ্যাঁ
white font দিয়ে দেন, টেক্সট কালারটা চেঞ্জ করে white দিয়ে দেন, তাহলে ভালো মতো বুঝবে।
টেক্সট কালার কই?
সিলেক্ট করুন, ইনভিজিবল গাইস,
আচ্ছা, as a because it's a correction, I have written downwards in this manner. পড়া তো যাচ্ছে না। আচ্ছা, এটা নিচে লিখি, ওইটা কেটে দেই, বেটার। এখানে একটা স্ট্রেট লাইন আকার একটা অপশন আছে, কোথায় জানো? ড্রয়িং,
ক্লিয়ার,
এটাই ভালো। Sorry, তোমাদের টাইম নিতেছি, but I really need to correct this because this is a significant error. Okay, এখন ঠিক আছে, সেই so that পরে থেকে প্রিন্ট করলে আর এটা হবে না। বুঝছো এটা কেন ডাউনলোড হবে সবাই? এভরিওয়ান?
Yes.
আচ্ছা, সেন্টার অফ মাস ও সেন্টার অফ গ্র্যাভিটি থেকে ইনশাআল্লাহ আমরা নেক্সট ক্লাসে পিক আপ করব। আজকে এই পর্যন্ত থাক, we are past 3 minutes. Thank you very much. আল্লাহ হাফেজ।